This is a question. Let's solve this problem together. So this question says steam is expanded in an isentropic turbine. Isentropic means that the delta S it is equal to 0, or means the entropy is constant at any state point. So if you have like a steam, so you know that the liquid line and vapor line, and this is steam, and these are the pressure lines. I just wanted to mention this. We have been doing this in pure substance chapter 3 many times, where P1 is greater than P2. So it is expansion process, of course, P1 and P2. So we have to locate the state points. So single inlet, single outlet. So I can draw the picture, a schematic for the, it's a little bit weird. So this is this is 1, this is 2, and steam is entering here and leaving here. So the condition for this one, it is saying that steam enters at 2 megapascals, and so P1 it is 2 megapascals, and T1 it is 360, and the steam pressure at the outlet, this is at the inlet, this is outlet, so P2 it is 100 kilopascals. Find the work done. So you have to find out the work done in specific units, kilojoules per kilogram. And you guys know that this is P1, which is 2 megapascals, and this is P2, which is 100 kilopascals. So let me show you that how would you solve. We know that the first law of thermodynamics, or which we also call as energy balance. So we will start from here and try to understand that how would you solve. So like E dot in minus E dot out equals to time rate of change of delta E of the system. So this is my system. Okay, this turbine is my system. This is the imaginary boundary, and this is equal to 0 for steady flow. For steady flow, this turbine is a steady flow case, so that's why it's the right hand side is 0. So we can apply this and see how. So when the steam enters, so H1 enthalpy, so any mass which flows into the device, it carries the enthalpy, and there is no other input other than the steam going inside. So, and we don't see any heat transfer in the mention, because this is an isentropic process, which is reversible adiabatic process, so heat transfer is of course 0. And on the other side, the outside, so we are getting the work out. So work out, or the power output, plus the mass flow rate in H2. So now looking into the steam table at, so in table A6, P1 and T1, so which is 2 megapascal, 360 degrees Celsius. So H1 it is equal to 3159.9 kilojoules per kilogram, and S1 6.9938. So this is kilojoules per kilogram Kelvin, and this is the entropy. Now let's see. We are interested in work output. So work or power output, rate of work, it is power, it is equal to m dot H1 minus H2. Now let's proceed for the P1. So the same table, if you take a look, P2 it is 100 kilopascal. So a this is the other table, a dash 500 kilopascal. So what we have to, since is an isentropic process, so let me show you. This is a6, so this is outside, and this is, let me show it. Oh, this is outside the, this is the state point inside, this point is 2, and this is, so from looking at the icenter, because s1 equals to s2, which is a reference point, so s2 also equals to s1 because of it as isentropic process. This is s, this is like temperature. So this is a very helpful point to locate the temperature and the other s1. So can you find out x2? So we know that x2 can be found by s2, which is sf plus x2 sfg. And table A5 will help us to find out x2, which is equal to 0.9397. And this is very helpful because we want to find out the h2, which is also equal to hf plus x hfg, I would say x2. So if you solve for this, you get 2538.9 kilojoule per kilogram. And look, this is our required formula to find out the power output. So if you plug in, let me copy this whole formula here and plug in these values to find out what is my power output. So actually this is mass m dot is not required in our case, so it is just W out, which is h1 minus h2. As you can see in the question, I did not notice this is the specific work output rather than the power outputs. So if you do the math, you get this answer, 621.0 kilojoules per kilogram. This is your final answer for the specific work output of the steam turbine.